My name's Chris. I was at MIT for a few rounds before they chased me away. As I mentioned earlier today, I'm in Ann Arbor. I'm not affiliated with Michigan. I'm in industry, but nevertheless, I'm in here in Wolverine country. I have three jobs. I'm the CTO of a public company called Cooper Standard. It's a global tier 1 automotive supplier. What we're going to talk about today with Liveline is an outgrowth of some R&D that we did for a couple of years, actually. So I'm running Liveline as the CEO slash pretending to be a data scientist, and keeps me fairly busy. So I think one theme I'd like to drive home today is really approaching data scientists as an engineer, not just a data scientist. And when we talk about what we're building, I think you'll understand that in some detail. At the end of the day, the Liveline team is really a bunch of engineers that are doing data science to solve our own problems. Many of us, even a year and a half, 2 years ago, didn't know a lot of data science. Personally, 18 months ago, I couldn't code Python and TensorFlow. I've now released a couple of core packages that we're using on the Liveline team. And, that really is the spirit of the group we put together. We're going fast, we're breaking stuff, we're learning by doing. And it's one of the reasons why we think this is such a cool area, because it's possible to do that, right? It doesn't cost any money to write bad code and find out what you did wrong. We just love being in a space where we can iterate quickly as we build some fun technology. So on that note, why don't I jump in here and tell you what we're doing. So Liveline, again, was born from a couple of years of R&D at Cooper Standard, the mothership. We've done pilots in 3 plants now, all in the US. We've got some fantastic results that we'll talk about. And based on that, we decided to go ahead and create a startup company exactly a year ago, and started it up just in time to shut it down for COVID. But fortunately, given our ties to the mothership, we were able to keep going on work, even though we couldn't be physically in plants, doing trials and so forth. And we got through that and really came back up towards the back half of last year, and finished up our pilots. And we are in the process of doing a global deployment right now. We're supposed to do 40 production lines this year. Hey,
Chris, I hate to interrupt, but your slides are coming across kind of small, and some people are having trouble seeing them.
Okay, let me try to redo this then. That's what I was afraid of. One more try. Sorry, I'm on a multi-monitor setup. This might be better, even though it's not optimal.
There we go. That looks right.
All right, sorry.
Yeah, if you just make that kind of as big as you can within the PowerPoint, that's more visible. If anyone's still having trouble, let us know. The chat is quiet. Go ahead.
Okay, very good. So, normally when I talk about Liveline, I'm talking to investors or potential other customers and do a little bit of song and dance. But I thought for this group, I'll just jump in and talk about what we're building. So this really gives a schematic for the overall stack and application. At the end of the day, we're trying to do real-time process control. And if you look at the right, in this case, I think the icons say that we're making espresso, which we certainly do a lot of anyway. When you interface with industrial hardware, typically it's through some kind of programmable logic control layer, PLC layer, very, very standard stuff in the industry. And we're trying to reach, through that layer and make real-time changes to process parameters, literally every second almost. And so, the question is, what's the easiest way to pull that off? And this is what we've landed on. I'm going to talk later about things that we tried that didn't work, because I think that's interesting sometimes. But this is really our approach. And so there is a real-time, online inference loop for this, using a trained controller that we'll talk about in a bit. We did have to do some work to develop a transport layer. So the way that we're passing data around the stack is very particular, because there are many sort of consumers of that data, one of which is the offline modeling. So we had to build a transport layer that we could live with, that could talk to industrial PLCs through standard protocols. That, as a data scientist, you might not be familiar with things like OPC UA, but it's very standard stuff in controls world, and that's the type of protocols we have to interface with. So we have to bridge that. But before we can run a trained controller, we obviously have to do the modeling. And the approach that we've landed on is a two-step approach. We are in an offline mode building physics models of the process, and those are nothing more than input-output models, where the outputs are variables that we care about, such as the dimensions of the product, or surface quality, or some different features that can really matter. I think later on today we're talking about LSTM autoencoders and great tools like that. That's in the zone of these types of physics models. So another phrase you probably heard is sequence-to-sequence modeling, and that's a lot of what we're doing. So once those models of the process physics are developed, then we get to put those into another environment where we are training controllers. And our approach right now is based on reinforcement learning. So you can think about these physics packages as going in as the engine for the environment that our reinforcement learning agents are interacting with. And then once those agents are trained and performant to the degree we want, those get put out then as a controller package that runs on the edge in the plants for inference, and is actually making the changes to the equipment. So again, the data science is sort of a two-stage process, and there's a lot of implications to that we're going to talk about today. And if I don't hit on something that you're curious about, happy to take questions as well. I'll point out that that there's a lot of ways to do many of these steps, actually, and we probably tried a lot of them and failed at many. But one of the other real lessons here is the coherent system design or system balance. And what I mean by that is it's always possible to get better models. You can invest more cycles in training and more cycles in inference, even in generating more sophisticated features out of your data set, and building more sophisticated models. The issue is we have to run in real time. We're trying to hit inference loop speeds on the order of a second. And so a second means going from a sensor in the equipment, sometimes, through a digital conversion, getting that up out of the PLC, transporting it, getting it into the controls package, doing any digital signal processing or feature creation we want, making the inference, detransforming into units that we need to set equipment parameters, feeding it through the PLC. So there's a lot to do in a second. And so we always have to be cognizant of the execution time of our data science pipeline and all that. And so there's this balance between having a controller that works good enough and having a controller that's to the nth degree more accurate, but is not practical in terms of the turnaround speed from sensor to actuator, if you will. So a lot of hard learned lessons in that, and that's driven a lot of the choices that we've actually made in our stack and design. So why would we do this? What's it good for? Here is the application to date. So if you look at the blue L-shaped box here, this is the type of process where we've done our piloting. We're talking here about continuous flow, chemical processing. We're taking polymeric compounds typically and combining them in interesting ways and extruding complicated engineered products that have metallic core inserts and 5 or 6 reactive polymers that are combined together, and trying to do that at speed with great accuracy. That description I just gave describes several industrial verticals that span hundreds of billions of dollars of revenue as verticals. So we're talking about wire and cable industry. We're talking about extruded polymers, weather seals, that sort of thing, and many others. So this is a very large category of industry that sits on top of all these different stages here, starting with refineries in the case of polymers. And those processes also have many of the same characteristics that we have to deal with, and as well as the intermediate stages of polymer production after refining and compounding of interesting blends of things. And at every stage there's lots of variability. At the end of the day, oil's a natural product, right? So no 2 barrels are the same. And at the end of this chain, we're essentially compensating for a lot of things that are very difficult to compensate for normally. I can tell you, we haven't done applications in real life yet, but there are discussions in places like food and beverage where they deal with natural raw material products and many analogous issues there as well. So again, we think that this problem statement is broadly descriptive. So I'll give you one specific pilot example to drive it home, and then we'll start talking a little more about tech. At the left, you'll see a product that we did as an early pilot. This is a sealing system that would go, for example, around the door of a vehicle. Aircraft would look, somewhat similar to this in some cases. You've got multiple polymeric materials. They're all reactive. They cure as the process runs. They're getting co-extruded together through dyes where the flows are combining in complicated ways, and very nonlinear behaviors in that. And then you have metal forming for the piece inside. You have extrusion, you have multi-stages of ovens and cooling, and there's heat transfer, and the chemistry is going on all this time. Very, very complicated. And to make it worse, the tolerances here are usually extremely tight, given what these products are. And there are thousands of product variations in the plants, and they change all the time because the designs get updated, the equipment gets modified, tooling wears out, it wears over time, or the raw material supply base churns frequently as our suppliers at places like Dow and Exxon, change their product offerings. So a lot of churn. That ultimately is why these types of processes have not been automated. And it's a difficult scenario for controls for all those reasons. And no automation means high scrap, high labor, high waste. All that means burning energy. These are very energy intensive processes. The waste is often not easily recyclable. So there's a huge footprint, environmentally that the waste implies. So the great need to do better. So this is ultimately our sort of aha moment. We tried really for a good year and a half or so to attack this problem in different ways. We'll look at a couple later on. We did it what I'll call the hard way, with some elbow grease by a team of very talented traditional controls engineers. And we were able, in one case, for one product on one line, to actually get some decent controls. The black line here is a smooth line, but it describes what you would see in terms of a day of production and variation, in this case, in a dimensional measurement. Think of this as extruded material coming out. The dimensions are getting scanned by a planar laser scanner, and this is one of those dimensions, right? So a lot of variation going on as different batches of polymers come through. So that the pink squiggly is not smooth, and that is the result of a human design controller. Believe it or not, that took about half the variation out from a dimensional viewpoint. The problem is it took about 3 months to figure that out. Because these processes are difficult to model, you can't tune them with nice, MATLAB toolbox tuning kits, the sort of things that us controls engineers would normally think of. It was very much elbow grease and burning a lot of time in the plants doing trials. Doesn't scale, right? And we got thousands of products and they change every day. And you can see the blue and the green were really about a year ago this month. The first results we got using some reinforcement learning design controllers that trained from scratch relatively quickly. And once we saw this, we said, look, this is the way we want to attack this problem, because now we have a chance to scale, constant deployment and tuning, updating of some very sophisticated controls in an affordable way without hiring an army of 500 controls engineers. So that's the point where we set up Liveline again a year ago today, and it really has launched us on our journey. All right. Nobody's commenting on the Mandalorian reference, by the way. I figured more out of the MIT crowd. All right. As I mentioned, it's more than just saving money in plants. There's really a big ESG footprint to what these types of processes are. They're typically require very highly skilled labor who have developed a feeling for how to control these processes manually. And these aren't glamorous jobs, and talent is an issue. It's not easy to convince young engineers that want to go stare at these touchy lines for a couple of years and get a feel of it before they can really take ownership of it. That's what it is today. So we're trying to change what these jobs are to manage these kinds of plants into a much more high skilled, much more interesting job in interacting with these intelligent systems. So that's the end of sort of the what we're doing and why part. We're trying to automate the creation of automation through reinforcement learning based controllers, and really hit a category of industry that's been tough to automate in the past. So before we go into more tech, any questions at that point? I'll take a few now. All right.
Great. I do have a question. So thank you for the talk. I'm just more interested in the reinforcement learning that you mentioned to do the control. So
Right.
can you talk a little bit more, like what is the reward system and how do you make sure it's taking the feedback?
Sure. Yeah, we can certainly hit on that. I don't have a particular slide on that, but I can give you some general feedback. So first of all, part of that is the secret sauce, right? We do have the ability to put some fairly complicated reward structures in. We do often use a combination of basically continuous measurements, like a dimensional measurement, but we also include in there a lot of very discrete, sometimes even Boolean types of flags for behaviors that we like or we don't like, that we want to penalize the model for. So I'll give you an example. You may want to penalize in your reward structure coming too close to the physical limits of how you can set temperatures or RPMs or amps on equipment. So we may make some nonlinear penalties in there for those kinds of things. So we often use a combination again of discrete variables and some categorical or Boolean flags on things. For those that have played with RL, right, that's a lot of the secret is sort of figuring that out. I'm going to come at the very end to one of our active areas of research, and that is finding ways to efficiently identify, the best combinations of those things. We do a lot of that by hand right now, but it needs to be automated. The problem is that reinforcement learning models can be computationally expensive to train. So we can't be too naive. We can't just make a menu of 100 variations and then go train them all times thousands of products and production lines. We can never afford to pay for that kind of computational power. So that is an active area still for us. We have things that we generally know work, but always room to do it better for sure. I guess the other comment I'd give you on that is you have to be very cognizant, as I'm sure, of the context that you feed these agents. So what is it that you're letting it see about the environment? In our case, we have the ability to look back and forward in time, because we have data that's streaming in, but we also have this physics engine that I talked about in our first stage of the model development that can constantly predict what it thinks is going to happen in the future. So we do give the agents the ability to see backwards and forwards in time, and that's also part of the the secret, if you will, to making this work. Does that help?
Yeah, that helps a lot. Thank you.
Okay. So why don't we talk about a few things that didn't work on how to solve this problem? Not all this is data science related, but sometimes it's educational to talk about other approaches. Probably 2 years ago, our first thought was, well, look, maybe we can just do some numerical simulations of these processes and almost use that in an open loop type of control setting where we generally speaking can set okay values of process parameters, given what's coming in terms of raw material that we sample periodically and measure the properties. That was the hope. The reality is these problems are way too hard to do that way. They're multi-physics simulations. There's a lot of computational fluid dynamics in the flow part of these processes. Worse than that, the materials are reactive. So rheology of the material is changing, based on heat and time and pressures. So not easy to do. Plus you have a lot of mechanical forces. You're pulling things down the line. You have gravity that's, sagging things down as you send it down the factory. Very, very tough to do. We made a valiant attempt, but in the end of the day, it just wasn't nearly accurate enough, nearly fast enough. Certainly could never use it in any kind of closed loop application. So we did give up on it. The picture here is a CFD simulation of, in this case, only two materials coming together and flowing in a die and mixing and coming out the end. So it's a little eye candy for you. So something else, that we spent a lot of time on and eventually abandoned were traditional control strategies. Many of us on the team, myself included, I was a controls engineering focus for my bachelor's and master's at MIT. There's a very mature toolkit of from that world. We did make a little headway on some of these, and in fact, that human design controller performance I mentioned earlier was in this first zone here with different flavors of PID controllers. You can make some progress, but again, because we can't model this thing very well, it's very difficult to predict and use the normal tools we want to use. So, rather than doing a lot of tuning on a computer in silico, we did a lot of tuning in meat space in the real world, burning a lot of time and energy, just very intensive and not practical for this problem. There's some other more advanced strategies to use, linear quadratic regulators, for example, get more towards this idea of truly optimizing over cost functions and time, in contrast to a PID. You also have things like model predictive controllers, which are used, have been used since, I don't know, probably the 80s in areas like oil and gas refining. But they have their issues too, and just are not ideally suited to this kind of problem. one of the issues with NPCs is you do have to run optimizers for those. And if you have enough time in the real-time loop, you can maybe get away with that. In our case, that was actually restrictive. And so we wanted to find some better methods. Ultimately, we, as I said, landed on the RL-based method. Again, not before trying everything else we could think of. We did, in fact, even go at one point, still trying to stay in traditional controls world, to do this like controls engineers. We tend to think, hey, if it's controls, Simulink, MATLAB is always a good place to do this work. And as many of you may know, and I hope you never have to know if you don't, MATLAB is probably not the advanced data science tool of choice. It's expensive. Integration, into your stack is not always clear, and how to do that effectively. So we abandoned that as well, and have gone to a pure runtime environment that you would be familiar with, right? Ultimately, the controllers are running in it's a Python TensorFlow runtime, right? That leads us to the right way, we think. So, we're using RL-based controllers. These have turned out to have a lot of strengths for us. Obviously, the notion of being able to sort of self-design controllers is fantastic. If we make it work, that reduces the number of controls engineers we have to have and gives us a feasible company, actually, and a scalable model. RL controllers can naturally accommodate some very sophisticated trade-offs in the objectives. So good question from Elva earlier. It's very natural to do that in these models. It's not so natural in other types of traditional control strategies. I will also point out that the infrastructure that it takes to do what we're doing turns out to be very useful for some other tasks, one of which is anomaly prediction. And we'll look at that on the next slide. That's not our product focus right now. We're working on the controls problem, but because of what we're doing, we can do that almost for free in terms of additional functionality. And again, I'll mention that on the next slide. And then also, because of the way we're doing this, it really opens the door for data scientists to work on controls using some familiar tools. If you're a controls engineer in industry, you have to know MATLAB, you have to know how to program PLCs and ladder logic and some really ugly programming things that I hope you never have to learn, but that's how it's done. And now all that work has moved into what you, I think, would consider to be some more familiar tools. And that is fantastic from a standpoint of accessing talent. There are some weaknesses. I mentioned the computational costs of training these models. It can be high. We've been very creative and sort of hand designing reward structures and choosing hyperparameters. Unfortunately, we can't afford to be naive and just start blasting, loops of training for tuning. So that it's an active area of work for us. I will also point out too, it does take a little care. If you haven't worked with streaming inference applications before, it takes some care to think through that. We train offline in a batch mode, and the things that you might want to do to your data in terms of pre-processing or feature creation, you have to be careful that those are applicable in a streaming environment. And to take one simple example, you can run certain sorts of digital filters that might have edge effects on the chunks, the batches of data that you feed it. Those edge effects might be trivial if you're dealing with a huge number of samples. That might be very significant if you're dealing with a small number of samples at once. So there is some care required to make sure that your feature processing pipeline is compatible with batch and streaming environments. And also the RL controllers do tend to be pretty active. And so we're still active in the best ways to handle that. We have several choices. All of them are effective. They have their pros and cons. We can regularize as we train the models. We can also just wrap these things in filters to smooth them out. We do, for example, put in some safety valves, if you will, in terms of if this, then that type of wrappers around what the RO models tell us they want to do to trigger, certain limits or clipping or whatever we want to do. But you do have to be careful sort of accepting the output from these models as you would with any output from any model, right? But in this case, it's physically altering hardware real time with some dangerous things. So just got to be careful. So I mentioned the ability to do some other interesting things with the stack that we built. We're focused on the real-time control at the left. That is a huge moneymaker. That is an area where I think it's been underserved so far, by data science in general. There are a lot of companies, both big and established, as well as startup companies that work on the right side of this page. A lot of cool work being done, but the approach tends to be different. And if you talk to startups, for example, that are doing anomaly detection or analysis of drivers of bad quality, many times they deal with ex post outcome information, and they're using classification algorithms or many other approaches to try to get some insights, and that's good work. What we're doing is different. I think we're in at a very low level. We have sensor level data as part of our controls engine. We have a physics model that is making real-time predictions, updating every second or so as to what it thinks the outcomes are going to be in the future, and those predictions are driven by a very low-level model, if you will. That we have that as part of the control loop. And so already, for example, in our controllers, we do have a variety of flags and analytics that are coming off those predictions that are telling us things like, we expect to go out of quality tolerance in the next couple of minutes. We're not exposing those right now as products, for example, but we could. I mean, the hook is already in there. And to put a front end on that and expose it, from an R&D cost, product development cost is almost zero for us. So those are the types of things that we can do using our stack, and is also why we're excited about the company and the way we're approaching it. I probably won't spend a lot of time on this other than to say that we went through many iterations of our tech stack. Like a lot of other companies, we're ending up with a hybrid on-prem, cloud-based approach. We're very agnostic to the cloud side of things. We can run wherever we need to. We're building things in a fully containerized fashion. We are all the interfaces here tend to be well-defined APIs. So it's, I guess, a modern stack, if you will, rather than being all hardwired together. Really, the only thing here that may be worth noting for our application, we did have to spend some time writing the bridge to the machine layer, and that's this OPC UA bridge that we see at the bottom of the plant boxes. We are actually using Kafka, for those that are familiar with that. It's basically a pub sub communication protocol, if you will, and we have bridged that into standard industrial communications protocol, and it turns out to be a great solution. It's very high bandwidth. It's very flexible for our application. We can have a lot of listeners to the data from the equipment, not just the inference models, but also all kinds of monitoring services and reporting services and that sort of thing. Archiving services, for example, as well. So it's turned out to be a really cool choice for us. And then the other point I think here to make is that we have to run inference in a self-contained way at the edge, which means on-prem at the plant. The reason is because no industrial operation will ever accept reliance on an internet connection to run their process in real time. And so we do have to be able to run on the edge for inference. And that is sort of a non-negotiable for us. So let me move to some lessons learned that may or may not be interesting for you. But the first one here, this is actually a Venn diagram. And it's a little cryptic, but it's supposed to be. The Venn diagram is a statement about skills and talent. And the circle to the left is the controls engineer, or the population of controls engineers. And the circle to the right is the population of data scientists. You know, maybe there's a 1 pixel overlap on this Venn diagram, but it's small. And that was really one of the you know, learnings we had early on when we tried to find partners to build what we wanted to build. And we were talking to data science companies and startups, but ultimately there was a large bridge and understanding between how control engineers view the world, view real-time process control, and data science. And you know, I don't think that was maybe unsurmountable, but we wound up really getting traction when we blended these teams very thoroughly, and even better when we started to get controls engineers that became a little more fluent in data science. You know, to the point of being able to write useful applications. That's when we really started making progress. You know, I think that to generalize this lesson, you know, that controls engineering could be any expert technical domain, right, for the application. But you know, getting these teams together basically 24/7 to co-design and iterate, you know, in sort of that agile software fashion, was really the way that we got this solved to the point we've solved it. So a lot of learnings for us. You can't outsource these kinds of problems to, you know, a pure data science organization and expect to get a usable solution, I guess. The second lesson I touched on a bit earlier. The pictures here, you know, refer to one, streaming inference, and two, you know, offline batch-based processing. We do a lot of both. We have to be very cognizant of what that means, you know, up and down our stack, and for the way we design the data science. But you know, at the end of the day, everything has to run real time on streaming data. The streaming data is not perfect, right? All the issues you would find when you pre-process offline data for training, you will find in the streaming data. You have dropouts on signals. You have you know, temporal issues, you know, with sampling, inconsistent sample rates even sometimes, if you haven't taken care to sort of handle those in advance. So a lot of things to consider. Just, you know, the practicalities of making it work. And then the third lesson refers to digitization. And you know, I think if you go into almost any industrial setting where the equipment is more recent than 20 years old or so, you will typically find data connections. You will typically find PLCs. You can plug in and get data, you know, right away. It doesn't mean you're ready to do what we're doing. And we did have to spend, in some cases, some significant time in thinking on what we needed in terms of digitization at the equipment level, and the best and easiest way to do it. You know, we can't engineer too specifically for that because we never know what types of protocols, for example, we find when we walk into different settings around the world. But it's something to be very cognizant of, certainly for our application. And you'll see the picture down below. That's John, and John is a fantastic programmer and data science, and he's doing the job of data science, sitting at a PLC panel at equipment. And we do as much of that as we do coding. But that's part of why we think it's such a fun thing. And then when it comes to data science in particular, I don't know if you'll find this relevant or not. I put this in here because we do recruit and hire data scientists actively. And these are some of the things that we see when we talk to people at different levels, even of education or graduate education or postgrad experience. From our viewpoint, right, from what we're trying to do, there are some things that it is very useful for data scientists to know about, at least be conversant in, if not somewhat fluent. One is digital signal processing, right? They need to understand what options are for bandpass filtering. They need to understand the importance of being able to work in frequency domains as well as time domains. I can tell you it is often quite useful to model our problems in the frequency domain. Probably most of you are familiar with what that means, but it means, doing things like fast Fourier transforms, or even better wavelet analysis, and getting out of time domain and looking at things in terms of, amplitudes across frequency bands and how those change over time. Rich source of information and often very effective to directly model on that instead of the time series data. Basic control theory, obviously, right? What does it mean to have a closed loop system? What do we mean when we talk about stability? For example, good to know. And then, as always, as you might imagine, a cognizance of the whole stack, right? What's the end-to-end concept? What are we doing in terms of the hardware layer? We do run inference at the edge, right? And we don't want to have to buy expensive equipment to do that. We'd love to be able to run inference on, Raspberry Pi if we can. I'm exaggerating a little bit, but we want to use cheap, throwaway, industrial PCs, right? We don't want to be buying, expensive, NVIDIA GPUs for that purpose. We love them for training offline, but not for this purpose, for inference. So, cognizance of the whole stack is important, but maybe the last one here is the most important. And that is really having a mindset of producing production code. We do find a lot, especially, undergrad or maybe, master's level data scientists, and they maybe done some interesting work. We always, ask to look at people's projects and code as part of the interview. And we'll find folks have done good work with, Jupyter notebooks, but maybe don't have much of a mindset yet for writing production code. So that would be things like, good practices for defining and using APIs, being able to write really clean object-oriented code, for example, and wrapping everything in objects instead of scripts and notebooks, and being able to document well, right, both within the code and without. Not as much fun sometimes as working on models, but really important to be a small company that is rolling data science into live production continuously. It's just critical that everybody is working in this framework. And so, I think about a data scientist we just hired in the last month, and we've been putting them through boot camp on some of those topics, so they can be effective and producing things that we can consume as a company, right? So, like I said, maybe all obvious stuff and not useful, but certainly consistent with what we've seen. So I think the last slide, and then we can just chat on what you want to chat about. As far as open issues for us at Liveline, technically speaking, I did mention about automation of things like tuning RL models. It's a big topic for us. We can do it. We'd like to do it more hands-off, more efficiently. We would like to do more in terms of automation of choices for our feature engineering. That also always needs to be as hands-off as it can be. We have the ability to process signals in many ways, including frequency domain analysis, We'd like to not have to make those choices every time, we build models with people. We'd like to automate that to more than we are today. I think, the notion of integrating RL controllers into our runtime is going to be an active topic for a while. I mentioned they can tend to be a little overactive. So how do we handle that? Do we do it by better regularization during training? Do we do it by wrapping them up in protective cocoons with if this and that rules or cascaded PIDs? All those things can work, but there's trade-offs associated with it. So it's an active topic for us. We have not yet built a global operations center. That's on our menu to do. It's not data science per se, but it is key to being able to do things like have efficient pipelines for deciding when to trigger retraining on models, right? As models begin to diverge from reality, do we take that as a signal to just retrain, or do we take that as a signal that there is an issue with the process, and how do we analyze that? That's all operations center level stuff for us that we're really moving into this year. Productization, that includes front end stuff. What are we showing humans in the plants about the system? What do they need to know to interact with it? What choices do we want to give them versus purely automating? Some really cool work going on there, as well as many other topics. So I think I'm technically coming up on my time slot, but happy to answer any questions now, or you can always reach out, and love to continue the conversation.